everybody. Welcome back to Chem 140. Today, we are going to be working on the rest of Unit 3. We're going to start and probably finish Units 4 and 5 because they're both like 10 slides long. And then that's probably all we'll do today. We're not gonna get to Unit 6. Even if we finish, we'll have covered enough content. And what else do I want to talk about? Oh, right. Yeah, I look over at the feed and I can see like, oh yeah, maybe you want to talk about this stuff down here. So there's stuff that's due tonight. Lab worksheet number 1 and quiz number 1 are both due tonight. That is a soft deadline. Thursday the 21st. Make sure that you get your materials in by that deadline. Tomorrow you will get one final reminder, basically just saying, hey, tonight is the hard deadline. The assignment closes. This is your last call. If you don't get it in by the deadline, you don't get it in at all. So make sure that you finish that assignment on time. Well, without further ado, let's just go ahead and get started here. So that's not PowerPoint. There we go. The last thing that we wanted to talk about in Chapter 3 about percent was a topic called percent error. Percent error is just a rubric of how close a number is to the correct answer. So maybe in the laboratory you were measuring the density of a metal or something, and you get an answer, and then I tell you the correct answer. And then you could say, oh, okay, well, I was 6% off, or I was negative 2% off, or whatever. And so that would just give us a little gauge of like, oh, you were very close, or oh, you had significant error. So this is just a technique and a formula that is used to help us understand the magnitude of error in measurements. Now, you're going to notice that my formula on this screen is missing these absolute value bars. Some people put an absolute value bar on the formula, but I personally don't. The reason for that is because if this number right here, the measured value, is less than the true value, then what you'll end up with is a negative answer, because a small number minus a bigger number is a negative number, right? And so with a negative sign on your percent error would mean is that your answer was less than the true answer. And if you instead had a positive... Ooh, I don't know what happened there. I think I tapped the screen. If you had a positive result for percent error, then your answer is more than the true answer. So that plus or minus actually tells you something. Which direction are you from the answer? You could think of it as like a number line, where your answer is at the 0 point. And if you were a little less than that, you'd be on the left side of that 0 point, which would give you a negative % error. Doesn't mean it's wrong, just means that your answer is less than the target answer. And so that information is useful. Why not include it, right? All right, so let's do an example here. Let's suppose that you were trying to figure out the density of aluminum, because in next week's lab you will be. Excuse me. A student measures the density of aluminum to be 2.63 grams per cubic centimeter. The true value is 2.71 grams per centimeter, or cubic centimeter. What is the student's % error? So using this formula, we could calculate the % error. Let's do that together over here. I'm just going to clear the red text real quick. And then I might as well just do that. There we go. All right, let me zoom in a little bit here. All right, so the formula for % error, again, is the experimental value minus the true value divided by the true value times 100% to make it a %. So our experimental value is 2.63 grams per cubic centimeter. The true value was 2.71 grams per cubic centimeter. And we're dividing by the true value again, so I put the number over here. Times 100%. Okay, I have to do subtraction up here, which means that my result will be the answer to this problem. Now, doing subtraction like this, not super easy. So the way that I do it is I do it this way. And then now I do subtraction. So 11 minus 3 would be, and since I have the negative in the up here, it's going to give me a negative answer here. So 11 minus 3 is 8. 6 minus 6 is 0. And 2 minus 2 is 0. And then I would round to the correct number of sig figs, starting from the right. Do I have a number in both positions? I do. So this would be my result for this calculation. And of course, they start with the leaf blower outside as soon as I start lecturing. Of course, why not? All right, fortunately, they're kind of far away. Now that I've done that calculation, this is what my calculation now looks like. Negative 0.08 grams per cubic centimeter divided by 2.71 grams per cubic centimeter times 100%. Why did I flip the numbers? The reason I flip the numbers is because if you're trying to do subtraction like this, it doesn't work, right? You have numbers that are too big. So you need to have the bigger number, the bigger magnitude number on top. So I switched their positions to do that, so that I could actually do subtraction. Because you could punch 2.63 minus 2.71 into a calculator, and you get negative 0.08. But how do you show that vertically? We can't do it this way. That's just a little trick to help you arrange the numbers so you can do the subtraction vertically, because you kind of have to for sig figs. Now that I get to this point, I can then do the division on the calculator, and what you're going to notice is that, oh, interesting, this number up here only has 1 sig fig, so my answer is going to be 1 sig fig. So I get, oh, and the other thing that happens is these units cancel. So our answer will just have %. And so when I do this, I get negative 2.952, but I only get one sig fig. So I'm going to write negative 3% error as my result. So as your answer, so our answer would have been this number right here, gets close to the correct answer, you start to lose sig figs on your error. And that makes sense because as you get closer and closer and closer and closer, no percent values care very much about sig figs. I just did a subtraction here, which left me to have only one sig fig. If I had done the subtraction and I had gotten two sig figs, like this is a 1 or something, then my answer would have two sig figs. As you get closer and closer to the true answer, it gets harder and harder to define your error because it's so small. So if our difference in our error is just in the last decimal point, we're not going to be able to identify very many sig figs. We're only going to get one sig fig as a result at the end. If I compared like these numbers, then I would get a significant amount of error because they are very different even in the hundreds place. So when I do this subtraction, I would, like if I did this, I would get a number that has 3 sig figs, and my error would have 3 sig figs too. So we care very much about sig figs. It's entirely dependent on what happens in the subtraction. Remember that 100%, this is exact. This does not affect your sig figs. This is important because you're going to be doing percent error on the lab next week, and I guarantee that if you don't have the right number of sig figs, I will just mark everything wrong. It is possible to lose all of your points on a lab because you didn't do sig figs correctly, so you gotta know how to do this. This is like the one opportunity that I have to actually assess your knowledge of sig figs because Canvas quizzes and exams don't do it. Canvas doesn't know what sig figs are, but because I manually grade all your labs, I do. So make sure you are following these rules. All right. So that's percent error. I'm going to give you another sample problem here to try. Here are some experiments where students decompose a sample and get oxygen. And the mass that they were supposed to get was this. So what I want you to do is tell me the percent error for each student. Okay. So you're going to have 3 calculations. They're all going to have different levels of significant figures based on how close or far away they are from the correct answer. So tell me the percent errors for student A, student B, and student C. And we'll go over the answers in about 3 or 4 minutes. See you in a bit. once you have an answer, go ahead and print it in the chat for me so I know you're done. All right, let's go over the result. That's not the right button. My mouse is not... Is the sensitivity just low or something? Oh, it's too high. That's what's going on. Hold on. I'm right-clicking. I need to be middle-clicking. Okay, that's much better. Okay. Sorry, technical difficulties. Okay. That should be enough of the problem for me to see to be able to do it. Okay, so the true value for all samples is 2.705 because it's a standard sample. What that means is we basically gave a sample that had been standardized and weighed out, and everybody got the same mass, so there wasn't any deviation there. So, let's see here. So, for student A, their result was 2.725 grams. The true result was 2.705 grams divided by 2.705. All right, so let's do the subtraction. So there's the first one. So I'm going to subtract and get that. These both go to the thousandths place, so I'm going to report my answer to the thousandths place. Oh, shoot. I'm sorry. Hold on. Thanks. Yeah, say that as soon as you can if you can't see it, because I sometimes miss that. I appreciate that. Last night I accidentally muted my stream. Like, I hit a button on the keyboard, and I just kept lecturing, and nobody said anything for 5 minutes. And I was like, seriously, guys? Why wouldn't you let me know this? So I had to go back and do it all over again, of course, because I was just talking to myself. But no, I very much appreciate being told right away that, oh, there's an issue. All right, so there's my result of the subtraction. I didn't write the times 100% in here, but that's okay. We were going to do that anyway. So now I'm going to do my division after I cancel out these units. This one I have to calculate, so let's see. 0.020, 2.705. And then times 100%. And so the result that I got for that calculation was... Did I type it incorrectly? Yeah, I did. Okay, so 0.73... Oops, 74% error. And it's positive because my result was larger than the true answer. All right, let's look at example B. I got to find a place to put my calculator here that isn't on the side that I can't reach. So for example B, we have 2.510 grams. The correct answer was 2.705 grams. Times 100%. So let's go and do the subtraction. This number over here is bigger, so I'm going to do my subtraction kind of upside down. And my answer will be negative. So 5. 10 minus 1 is 9. 6 minus 5 is 1. So that's my difference there. So now I have negative 0.195 grams over the true answer times 100%. The units cancel. And I get negative 0.195, 2.705 times 100%. And for that one, I get negative 7.21%. All right, so let's do C now. Oops, it's not scrolling. How come? There we go. And for C, you get 2.801 minus 2.705. 2.705 is the correct answer, times 100%. So let's do the subtraction. And you should get that. That's 2 sig figs, so my answer is probably going to have 2 sig figs. Get my grams to cancel. And we'll punch in the calculator. 0.096, 2.705 times 100%. 3.548, so I would write down 3.5%. Sig figs are tricky, but you are following the same rules every time, so make sure you are doing the subtraction rules. It's all a part of this class, is learning the rules for sig figs. And so when you're learning and starting out, that's what you just had to do for a while. You look at a problem, say, okay, what's my first thing I'm doing? I'm subtracting. What are the rules for sig figs for subtraction? And then do them. Remember, addition and subtraction is decimal places. Multiplication and division is number of figures. Can't stress that enough. And if you need to review, you can go back and review the lecture for Chapter 2. They are all posted on YouTube forever. All right, I believe that is it for Chapter 3. Is that it for Chapter 3? If there is, there will be a little audio jingle at the end here. Hooray! There you go. For subtraction, does it have a rule for zeros? I don't know what you mean by that. So the subtraction rules deal with decimal places. So if both your numbers go to the hundredths place, you can do that. But if your numbers do not go to the hundredths place, and they go to different places, you're going to have question marks in there. Again, review the slides for Unit 2. Let me get the Unit 4 and 5 PowerPoint up here. Yeah, there's only 11 slides to this, so we're gonna finish very early. All right, so Units 4 and 5 are one section each in the supplemental text. And so I combine them because there's really no reason to have an upload that's 4 slides and an upload that's 6 slides because there's only like 10 slides here. We're going to talk about density. Density is just a relationship between a mass and a volume, but the applications of density are very, very, it's very flexible. You can use it for all sorts of things. So we're going to explore some of those properties here. So let's define density. Density is the ratio of an object's mass to its volume. Depending on the phase of the matter you're examining, the mass is going to always be in grams, but the volume may be in liters or milliliters or whatever. And so we have differentiated phases into different units as shown here. Now, the reasoning for this is because cubic centimeters tend to be easy to manipulate. So if you have a cube, you can easily get a 1 centimeter by 1 centimeter by 1 centimeter cube of a material with a little bit of effort. But for a liquid, that's almost impossible because liquids flow and they occupy the shape of their container. And so we don't want to use cubic centimeters for something that doesn't want to be shaped into cubes. We instead use milliliters. And yes, these are the same thing. So centimeters cubed and milliliters are equivalent. Remember that 1 cubic centimeter is the same as 1 milliliter. For gases have a very low density. If we did grams per milliliter, you get this really small decimal. So we end up doing grams per liter because air and other gases are very, very light. I think we calculated yesterday. Oh, excuse me. I think we calculated yesterday that a 2-gram sample of air was like 1.75 liters or something like that. All right. Now, I'm going to show you a density column here, but the way that density physically manifests itself when substances with different densities are mixed together, if 2 objects are insoluble in one another, and they have different densities, the lower density object will float to the top, and the higher density object will float to the bottom. I guess it doesn't float to the bottom, it sinks to the bottom. So, I'm going to show you this density column video. I gotta get the arrow back here. I'm going to have to capture the window. Oh, yeah, we have music here. So I will shut up and let you guys watch the video. Boop. That's probably cropped enough. We'll just make it bigger. That's too big. There we go. Alright, so here you go. This is a density tower out of common materials. So I'm going to hit pause and just have all the materials listed on the screen here. So these materials are, with the exception of the glass vase, which is what everything is held in, these materials are arranged in order from the highest density to the lowest density. So honey has the highest density, lamp oil has the lowest density. And we're going to put them in the container in this order. And then we're also going to add other things. We're going to add adult supervision, which has no density. But we're also going to add a bolt, popcorn kernels, dice, cherry tomato, beads, etc. So these are all objects that aren't liquids, but what they're going to do is they're going to fall into the container once we put all the liquids in there, and then they're going to sort themselves by density too. For example, a ping pong ball has a specific density. It's mostly whatever the density of air is, right? So it'll fall into the column wherever the density of air should be. The cherry tomato is mostly water, so it's going to sink past all the things that have a lower density than water, and then float on the first thing it comes into that has a density higher than water. And so let's see that in action here. So here's all the solutions. Food coloring has been added to some of them just so that you can see what they are, because water does not normally look green. If it does, see your doctor. And then we're going to just slowly add in this column, so here it goes. I hit the button again. That might be what I'm doing. Hold on. Oh, I found it. So when I hit the space bar, it mutes me. That must be what I did. I might have tried to load a video last night, and I hit the space bar to stop it, and it didn't work. Because I was over here resizing it in this thing. Okay. Well, thank you. We've solved the mystery. I can do this, I guess. It sounds very weird. There we go. No, that wasn't a test. That was just me doing the same thing I did last night on accident. Okay. So, let me say that again here. So, these substances are sorted by their density. And you can see that they're kind of trying to mix, but because of how they were added carefully, they don't mix together appreciably. You still have a region where it is mostly one substance. So other stuff on the right here, like the bolt was more dense than all of these because it's metal, so it sank all the way to the bottom. But the popcorn kernel was more dense than water or dish soap or milk or maple syrup, but not as dense as corn syrup. So it sorted to be here. Here's the dice, which is made of plastic. You can barely see it, but you can like see the numbers right there. There's our tomato. The beads, which you can kind of see on the side here. And then the ping pong ball, which is full of air, is on the top. So these all sorted based on density. And it's kind of cool. So there you go. All right. Now, this is the same premise by which boats float. So if I have a boat, so here's my boat. Well, let me draw the ship here. My boat is very triangular because it's an aircraft carrier or something like that. So there's my boat. And then we have the water outside it. I guess it goes on the front of it, so I should draw it there too. Now, if the boat is made of steel, you might be asking yourself, well, how the hell does it float? The density of steel is way higher than the density of water. Now, if this was the ocean, the density of the water in the ocean would be about 1.0 grams per cubic centimeter. Closer to 1.1 because the salt increases the density. So our ship needs to have a density less than 1.0 gram per cubic centimeter in order to float. How the hell do we accomplish that? Well, if you make a ship that is big enough and open enough, then the displacement of it will be mostly because of air. So you'll see things like aircraft carriers and military naval vessels and even just like cargo ships. Like it looks like they're barely over the surface of the water, but there is a significant amount of ship underneath in the hull, and it's all just air. And so that air contributes to the density of the whole thing, or the ship as a whole. Now, if you were to do something like, say, this, okay, that was a little extreme, I guess. If you were to do something like this, and then the water gets inside the ship, then this happens in here, and it all fills with water, and then this is not true anymore, and the ship immediately starts floating. How do icebergs float? Okay, well, here's our water. And here's our ice, so here's our glacier. How do icebergs float? What's the density of ice? And what's the density of water? Ice's density is less than water. In fact, water and ice are a very bizarre sort of phenomenon where ice is one of the few substances to have a lower density in the solid phase than in the liquid phase. Very few other substances do this. And so an interesting consequence of that is that in the winter, in, like, say, a lake, your ice freezes at the top and then floats there. So your ice would freeze over, and so your fish down at the bottom I can't draw, so there you go. There's my fish. They're floating around at the bottom with, like, some seaweeds and, I don't know, other stuff. Bubbles, whatever. So the ice floats at the top because its density is lower. And the rest of the water stays unfrozen. Because the water that remains water has a higher density, it sinks to the bottom. Now, if this didn't happen, what would happen is that ice would freeze at the top because it's colder up there. Then it would just fall to the bottom and crush this guy. So all of our sea life would be destroyed. And then the ice at the top would freeze again, and it would fall down. It'd be like Tetris, but deadly. And you just end up having a giant solid block of ice for all water if the surface of the ice was more dense than the water it floated on. Now, fortunately, that doesn't happen, so our fish can survive through the winter, and so that our oceans don't completely thaw through or frost through. Now, that's just a coincidence. Like, for whatever reason, water does that. How it arranges in the solid phase is a lower density than how water randomly arranges in the liquid phase. There are probably also some air pockets in ice. I think that that's inevitable, but the primary reason that ice floats is because its density is less. It just happens to be less. So I'm going to give you this example to practice with. I'm going to let you do this because it's pretty simple. I'm going to give you a sample of olive oil. Here's its mass and volume. I'm going to give you a sample of water. Here's its mass and volume. Which floats? Draw a picture of the result. We'll go over the answers in about 2 minutes. Sorry, you probably heard me clicking through folders to get to the schedule here. I just want to see where we are. No, we're right on track. Okay. One more minute to finish up your calculation and your drawing, and then we'll go over the answer. I was sitting there trying to figure out how to troll you guys by like drawing on the screen during that entire break, but that was the best that I came up with. Was to just pretend I was drawing and then write just kidding. So let's draw a diagram first of a container. And then those are going to be my two solutions. One of them is water and one of them is oil. So let's figure out the density of the oil. So its mass is 18.6 grams. And its volume is 20 milliliters. When I punch that in the calculator, I get 0.930 grams per milliliter. Notice that these units don't cancel out, so I have to keep them. Very important with density. Make sure you are keeping your units along with it and that you aren't canceling them out, because that's what we've been doing so far. Sometimes the units don't cancel. Now I got density of water, and you'll notice that, oh, well, its mass and its volume are the same. So I get 1 gram per milliliter, and a cat. Hi, Maya. Yeah, I'm doing chemistry. Oh no, she's coming this way. Which one has a higher density? Well, 1 gram per milliliter is higher than 0.930, so the oil is going to go like this, and the water is going to go down here. All right. Oh, excuse me. I have a frog in my throat, even though I'm drinking water. Let's do a more complex calculation where we use a density value to answer other questions. Because if I know the density of something, I could figure out the mass of it or its volume given the other thing. So let's do that. Oops. Well, there's the answer. I showed you the answer. All right. So the number I quoted before for ice apparently was a little bit high. This is the actual density of ice, 0.9167 at 0 degrees Celsius. I actually looked that up to do this slide, I'm sure, when I wrote this. Let's suppose I have a glacier with a volume of 35,720 liters. It's not a very big glacier, it turns out. What would its mass be? Okay. Well, how do we do that? Let's go over to this problem. I don't know why. It recaptured it because I'm on a different slideshow. Probably had the old one there. All right, so I know that the density of the ice is that. I had to cough there, so I was just trying to hit mute. Now, whenever I write my units like this, keep in mind that that is the same as writing them like this. And what that means is that this becomes a conversion, and I can flip this around however I want to. So if I have a volume in liters, and I want to figure out from the mass of that glacier what its mass must be, and for mass let's do kilograms, because masses of large objects are probably more appropriately measured in kilograms. I could turn liters into milliliters, which is the same as cubic centimeters. And then once I know cubic centimeters, I can then turn it into a mass, right? I just use this conversion. And that conversion would be, for every 0.9167 grams of ice I have, that's a cubic centimeter. The other conversions are pretty straightforward. Like, we can do liters to milliliters. There's 10 to the minus 3 liters in a milliliter. And then these are just equivalent. And then I can do grams to kilograms. Maya. Oh my gosh, she's right there. Fine, Maya. Maya wants to say hi. Say hi. Say hi. There, you said hi. Can I go back to work now? Oh my goodness, she said hello. She said hello. It sure sounded like hello to me. I don't know if you heard it. I've been trying to teach her to say hello. Huh? Huh, Maya? That's the wrong color. There you go. Maya. Oh my goodness. All right, so let's do our dimensional analysis. We're going to turn liters into milliliters. We're going to turn oops, I got to cancel. We're going to turn milliliters into cubic centimeters. And then this right here, this is where our density is going to go. So you can see that I've set up the units such that I can just put the numbers right in there. And then finally, grams to kilograms. So this will be the mass of our glacier based on this information in kilograms once we run the numbers here. So let's do that. So milliliters to liters, in 1 milliliter, there are 10 to the minus 3 liters. We said that a milliliter and a cubic centimeter are the same by definition. This right here is the density of ice, so I'm just going to put these numbers right in there. 0.9167 grams per cubic centimeter. And then finally, a kilogram is 1,000 grams. And so I'm going to multiply all these numbers together and do the division. Ten to the minus 3 times 10 to the positive 3 cancel out. And so the result that I get in kilograms is 32,744.524. This number as written has 4 sig figs, and so does this number. So my answer should have 4 sig figs. Now, you might think, wow, a 32-ton or metric ton glacier is probably pretty big. 35,000 liters is not a huge volume. Most glaciers would be like on the order of megaliters, so millions of liters. This is just 10,000. All right, any questions on how we did that calculation? Now, remember that when we're doing density, density is equal to mass over volume. And so, if you have one of these things, you can always solve for the other one by using the density. You're just going to have to use it in some relationship as shown. So I could instead give you the volume, or I'm sorry, we did volume. I could give you the mass, and you'd be asked to calculate the volume. So in this first spot, you'd just put mass, and then you'd go through the same decision tree, connecting your units in your flowchart. So I did this in grams, but that's the same number. All right. Oh, question. Do we not add the 10 to the 3 or 10 to the minus 3 in the calculator? I don't really have a way to show you this, so let me do this. So, depending on your calculator, what calculator do you have? Can you tell me that? Because what I'll do is I'll just go to a Google image search and I'll find it. So TI-83 is the most common. Because you do have to add those numbers into the calculator. So what I can do... Let's see if this works. Yeah, there we go. So I have a calculator here, which I just copied and pasted off the internet. If I zoom in, there's a button right here on this calculator that says EE. And so this right there is the button that you want to hit. And what that will do is it will print on your calculator. So like you might type in, you might want to type this number, for example. So you would type in 1, you'd hit that and it would print a little E. And then you type in -3. And what the E represents... Oops, hold on. Is times 10 to the n. Where n is the number that you were going to... Or, sorry, this is a caret. Times 10 to the whatever power that you're about to type in. So you have a sharp calculator. So you might have a button that says EXP or times 10 to the n, and you just push that button. And it will put some character. Usually the character that's put is an E. You have EXP. So hit that button, and it will probably print a small capital E, or it might print times 10 to the... But then you type in the exponent after that. You don't need to type in the 10 yourself. The 10 is already implied. So when typing in, say, 5 times 10 to the -3, you would type just 5 here instead of 1. You go 5e -3. If you were just doing 10 to the -3 by itself, that's the same as 1 times 10 to the -3. So you just do 1e that. All right. Goodbye, calculator. Oh, I have to get rid of that layer, too. Deleted. Deleted. All right. Cool. All right. Let's suppose that I wanted to find the volume of air with mass 32 kilograms. Yeah, no problem. And then air has this density. What would its volume be? I want to let you try this for a few minutes. And then we'll go over the answer together in just a moment. Okay, so take a crack at it. All right, we have one answer coming in. We'll go over the answers together in just a second. Then we'll take our break. All right, so let's go over the answer. So I know the density of air is 1.29 grams per liter. And I want to figure out what volume of air must have a mass of 32 kilograms. So I need to go from kilograms to volume, which would be liters. Well, if I turn kilograms into grams, that's pretty straightforward. And then I can turn grams right into liters using the density, because 1.29 grams of air is 1 liter. So let's do that. We're going to turn kilograms into grams. And then we'll turn grams into liters. All right, let's do the numbers. 1 kilogram is 1,000 grams. And then the density of air is 1.29 grams per liter. You'll notice that, though, the units are upside down here, so I got to make sure I put them in the right spot. 1.29 grams per liter. Because remember, I can flip conversions however I want to. So 32 times 1,000 divided by 1.29. So the volume I got was 24,806 liters, which would be 2.48 times 10 to the 4 liters. So I think that the answer that was given, 24.8 there, I think that was for 32 grams of air. We want 32 kilograms of air. So make sure that you did this part in your calculation too. These types of problems are going to be just like unit conversion hell. And that's sort of just how these problems are in the real world. Like, these are real world problems that we're giving you now. You might want to know what the mass of 32 or what the volume of 32 kilograms of air is, because you have a chamber that is some volume large, and if it has too much air in it, then it would take too long for your vacuum pump to remove it or something like that. So these are all problems that could come up in engineering or in like in the world at large. All right, we are due for a break because it has been an hour. I went over a little bit, but that's okay. So let's put this on the screen. You always need to convert to the units of whatever the question is asking you. If there are not units that are given, so for example, for that problem, I'll go back to it real quick. That problem just asked for a volume, so you need to get to a volume. But in order for you to get to the volume, I know what the volume is per gram right here. So I need to have grams somewhere in my conversion so I can get to liters. So I must convert kilograms to grams to continue. From here, you could turn this into whatever unit you want to. You can do anything you want as long as it's a volume. I will try to be more specific, but for these problems, I'm just trying to get you to get into the process of doing all of the conversions. All right, I'm going to put the Metroid music back up. I just got to find it wherever it is. There it is. All right. So we'll start the timer. And I'll see you in just a little bit. If I could find the music that I'm going to play, where the hell is it? There it is. Hey, look at that! That's exciting, right? How often do I do that? Yay! Alright. Where did my slides go? There we go. Okay. Alright, so what I want you to do is to do these 3 practice problems for density. So the first problem, I have gold. Gold is a density of 19.3 grams per cubic centimeter. Gold is one of the more dense substances we have. Let's suppose that you have 329 grams of gold. What would its volume be if you melted it down into like I don't know, a framework or a mold or something in cubic centimeters? I have a carbonated beverage right here. It's Polar Seltzer. Advertising for my friend Dan, who loves this stuff. Let's suppose its volume is 355 milliliters and its mass is 361 grams. What's its density? And then I have a boat. The boat has a volume of 65 times 10 to the 6 liters. What's the maximum mass it can have and still float in water if the water's density is 1 gram per milliliter? Remember how floating works. You have to have a density less than what you want. So find out what would give you a density of 1 gram per milliliter, and then say, oh, I just need to be under this. Okay? So there's 3 problems for you to try. I'm going to hit mute and go get some more water because I drank all mine. And we'll go over the answers in this will probably take like 7 or 8 minutes, okay? So go ahead, get to work. Type your answers in the chat when you get them, and if you have any questions, let me know. How are we doing? Anyone have any questions on these? Ah! My cord got caught on the keyboard. Very professional, I know. Let me know. I'm going to give you about 3 or 4 more minutes. If you have any answers at all, go ahead and post them, though. Let me know how far along you are. Milliliters and cubic milliliters. Cubic milliliters is not a unit, so if your answer is asked to be in milliliters, just give it in milliliters. So, like, for the first one, I asked you to give me the volume in cubic centimeters, so give it to me that way. For the second one, I want a density. It's a liquid, so use the appropriate density. And the third one, I asked for a mass, so you can give me any mass you want. What are the units for density? Well, so it's a beverage. So what were those units? They're a few slides back. And I'll give you a hint. You don't have to do much work for the carbonated beverage problem. All right, let's go over the answers here. Let me clear this screen and then we'll do that. Let's get the first problem in here. There we go. All right, so gold has a density of 19.3 grams per cubic centimeter. And I'm given the mass of gold, 329 grams. So I want to get to volume. So I want to go from grams to cubic centimeters. I give you this density right here to do that. So we know that 19.3 grams is equal to a cubic centimeter. So we'll just set up the units to cancel out grams and turn it into a volume. There you go. And then I'll put the numbers in. 19.3 grams per cubic centimeter. And we'll go to the calculator. 329 divided by 19.3, 17.04663. That's way too many sig figs. So let's look at our sig figs here. 3 sig figs, 3 sig figs. Ones are exact. So I should report 3. There's the answer I got. Hopefully that's the answer that you got. For the second problem, I know the mass of the beverage is 361 grams, and I know its volume is 355 milliliters. If I divide the two, that's the density. So let's do that. 361 over 355 is 1.0169. If I check for sig figs, everything has 3 sig figs. So my answer should also have 3 sig figs, and I got 1.02. The units didn't cancel out, and those are the units for liquids. Remember, liquids have a density of grams per milliliter. Oops. And then we have a boat. My boat has a volume of 65 times 10 to the 6 liters. That's not proper scientific notation, just be mindful of that. It should be 6.5 times 10 to the 7. But if you're writing out numbers in engineering notation, they tend to make their exponents just be powers of 3. So you might see this. So I want to figure out the maximum mass it can have and still float in water with a density of 1 gram per milliliter. So if I can turn my volume into a mass using the density of 1 gram per milliliter, I will find the theoretical maximum. So we need to turn liters into milliliters because our density is in grams per milliliter. And the density is 1 gram is 1 milliliter. And we know that 1 milliliter is equal to 10 to the minus 3 liters. So we can now do that dimensional analysis. So we'll turn liters into milliliters. We'll turn milliliters into grams. And so I'll get the mass in grams this way. Now I got to run the numbers. And when I do that, I should get, let's see here, I'm just dividing by 10 to the 3. So this would be 6.5 times 10 to the 10 grams. Which is also the same as if you did this in kilograms, you should get that. So what that means is that this is the maximum that you can have for a ship that will float in this density of water. So if you're loading your ship and the ship's total mass exceeds that, it'll sink. Its density will be too high. So you can only put so much stuff in the hold, because as you do that, you're displacing air with more dense material. And obviously you don't want your boat to sink, so there is an upper limit to mass. All right, I believe that is everything for the density chapter. So you're going to be doing an experiment with density next week in the lab that we have set up for you. So we'll go over that more in more detail on Thursday. All right, let's briefly talk about temperature. The temperature lecture is just kind of, hey, let's get introduced to temperature units. And we only really have like 10, 15 minutes left anyway. So I'm going to show you the 3 temperature scales, and then you can do the conversions on your own if you'd really like to. All right, so here we go. There are 3 scales that we are going to interact with for temperature conversion. And of these 3 scales, we really only care about 2 of them. Those 2 scales are on the right here. Let me put all the units on the board here really quick. Fahrenheit, oops, I don't want that yet. Fahrenheit is really only good for confusing Canadians. So, like, if you have a friend in Canada and you say, wow, it was really hot out today, and they go, oh, how hot was it? It was like 85 degrees. They will go, holy shit. Because they'll think of 85 in Celsius, because they use Celsius in Canada and most of the world. I was going to say the civilized world, but after the what's it called? Yesterday. Inauguration, there we go. After the inauguration yesterday, I feel like we might be back in the civilized world, so who knows. But we still use Fahrenheit here, and Fahrenheit is bullshit. Fahrenheit is not a useful unit in chemistry, and the reason for that is because the number of degrees between the 2 bars that we have set, which are the boiling point and the freezing point of water, is kind of a weird number, 180. Celsius is a little more useful to us because we have set the freezing point of water and the boiling point of water at nice round numbers. Water freezes at 0 and boils at 100. And there are 100 degrees between that. The Kelvin scale does not have those numbers line up very nicely, but you'll notice that there are 100 intervals between freezing and boiling, just like Celsius. And so the conversion between Celsius is 1-to-1. 1 Celsius is equal to 1 Kelvin. Whereas over here, there are 180 degrees. So 1 Celsius is equal to 1.8 Fahrenheit. Again, that's dumb, so we don't use Fahrenheit, right? Now, why the heck do we care about Kelvin? And the reason for that is because at the very bottom of the temperature scale is a phenomenon that we care about, and it's called absolute zero. Now think for a second what absolute zero might be. Think about why we would call it that. Why do we want to call something absolute zero? And the reason for this is because of how temperature is actually defined. Temperature is the movement of molecules. So if you go outside, it's cold, but the air around you is moving at the molecular level. And those particles move on average at a certain velocity. That velocity corresponds to temperature. And if the molecules are moving faster, then you perceive that as warm, because the molecules then hit your skin with more energy and they impart more energy to you. Whereas if it's cold, they impart less energy and you actually have more than them, so you impart your energy to them. And so on and so forth. That's the short version. We're going to talk more about temperature and gases and stuff like that in 162. But for our purposes, for the Kelvin scale, we actually define the lowest possible temperature as 0 Kelvin. So at 0 Kelvin, all molecular motion ceases to be. It just completely stops. Which means that all molecules will be perfectly still and have no kinetic energy at all. Therefore, they have no ability to transfer energy because they aren't moving. And we call that 0. So that temperature would be 0 Kelvin. Now in Celsius, that's a weird number because we have arbitrarily put Celsius on some point that means something to us, the freezing point of water. This is also another sort of arbitrary point. It just happens to be the lowest possible temperature we can get to. You'll notice that this number and this number are exactly the same, again, because 1 Celsius is 1 Kelvin. Over here, it's like minus 454 or something like that. Those are the lowest possible temperatures that you can reach. Now that's a good question. Is 0 Kelvin even possible? So if 0 Kelvin represents all of my molecules being stationary, completely still, I would have to isolate them from the rest of the universe. So if this was 0 Kelvin, and I insulated this box around it, out here would be not 0 Kelvin. And what that would mean is that molecules would bonk into this box, transfer their energy, and that energy would seep inside. And then eventually these molecules would receive that energy, and they would also not be at 0 Kelvin. So without a perfect insulator, which does not exist, we cannot insulate atoms to be 0 Kelvin. Because we cannot perfectly insulate something from heat. Now, we can get really darn close to absolute 0. So, like, I think the closest we've gotten is like this, 0.04 Kelvin. And so, like, this would be at CERN in Switzerland. CERN, Switzerland. I don't know if Switzerland is SW or SZ. Whatever. Now, it turns out that the average temperature of the universe is about 4 Kelvin. Which, interestingly, that means that the coldest place in the known universe, Switzerland. Specifically inside the device that was used to cool this all the way down. But yeah, the coldest place in the known universe is right here on our planet in Switzerland. Now, in a black hole, everything is moving really, really, really damn fast, presumably. I don't know what happens when you get in there. Now, theoretically, there could be other pockets of the universe where everything is insulated very, 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 very far from any other matter, just by virtue of it being very far apart. But we don't know about it, so yeah, not all of Switzerland gets that cold. Like, it would be, you could not go outside at that temperature. You would just immediately freeze and die from hypothermia. But specifically inside that research lab, inside the chamber where the experiment was done, and I don't even know if it was Switzerland. I just assume it was Switzerland because that's where all the crazy science is done. Like the Large Hadron Collider and stuff like that. There is another use for the Kelvin scale. And the Kelvin scale puts the 0 at the lowest possible temperature. So not a temperature that we can theoretically reach. Celsius, on the other hand, puts the 0 point at the freezing point of water, which is a reasonable temperature. You can go outside and function with difficulty because it's so cold at 0 degrees Celsius. Now, if you were using a equation, like suppose I had this equation here, and I asked you to put in a temperature for this equation to solve for whatever n is here, and you input this number, what happens when you do this calculation and you divide by that temperature? What happens when you do this calculation? Yeah, exactly. Everything blows up, and you destroy the universe, and this is what we're left with, a void with nothing in it. In fact, it would blow you guys up too, so there you go. And I guess I'm included in that, aren't I? Yeah, if you divide by 0, this is what happens. Everything goes away. It's gone forever, right? You can't divide by 0, it's undefined. So let's put everyone back. There's you guys. There's the slide. So you can't do this, obviously. This is not okay. So you cannot use Celsius in calculations because the calculations would break around the freezing point of water. That's kind of arbitrary, isn't it? So instead, we must use Kelvin in calculations. Now, that's not going to come up, I think, in this class. When you get to 162 and we start doing thermodynamics, where we start measuring the properties of how substances transfer heat and heat transfer in a chemical reaction, then suddenly this is very relevant. We need to know about temperature and that we can't use Celsius for any calculation where we just input a raw temperature. For all those calculations, particularly the gas laws, but many other things too, you have to use temperature in Kelvin. So that's why Kelvin is very relevant to us, because the 0 point is at a place that's unreachable. Now I'm going to clear all this text off the screen. There is one more scale that I do want to briefly talk about. So if I draw a line between these two are related, and this one has the absolute 0. There's also an absolute 0 scale for this temperature over here that relates to Fahrenheit, but I haven't put a letter in for it. Could you tell me what letter goes in the blank there for that temperature scale? I'll give you a hint. Somebody already got it. What letter could go there? I don't know. Do you have the right answer? No. No, you don't. This is actually called the Rankine scale. And at 0 degrees Rankine, we set the absolute 0 of Fahrenheit to be 0 Rankine. And then you just scale it for there. So the freezing point of water would be 454 degrees Rankine because this was minus 454. I stopped writing. I don't know why it stopped doing that. That's okay. Okay. Anyway, that's my temperature joke. I do all of that just to get you to go, oh, it's you because it spells fuck, huh? Ah, that's funny. And then I buzz you because it's wrong. All right. Here are the formulas to get between various temperatures. Honestly, committing these formulas to memory is not super useful. I would just go to Google and type it in, like, what's 37 Fahrenheit to Celsius? And it'll tell me, oh, that's like 5 Celsius or whatever. Or 2 or something like that. I think that that's much more useful, but here are the temperatures, just in case, or the formulas, just in case you wanted them. For these equations, the conversion factors are all exact. What that means is that however many decimal points you put in is how many decimal points you'll get out. After you do the multiplication, of course. But for Celsius and Kelvin, you only get to go down to the hundredths place if you use this expression as written. Now, there are more exact numbers. So, for example, if I wanted to get the thousandths place, this is actually what I've rounded 273.15 from. So if I wanted to go down to 1,000th of a degree, I would need to use this one instead, and so on. Okay, so these up at the top are exact, but down at the bottom, these are approximate. So that way you know what the correct scale is for temperature and how to get the correct sig figs. Because, of course, we care about sig figs in all of our calculations. Generally speaking, temperature isn't going to be the limiting factor unless you're working at a very, very, very low temperature. I have never heard of the KFC analogy for temperature. That's really clever, actually. I like the expletive joke that I have there, but KFC is also really good. Now I want chicken. Oh. We already talked about absolute zero, so I'm not going to go over that. And I'm not going to have you convert these temperatures because that's just kind of busy work. You could just throw into Google if you ever need to. So if you really want practice, you could do these on your own. But I'm going to say that that's all we're going to do. And we're out of time anyway, so that works out great. Now, you have a quiz due tonight, but I am going to assign you a second quiz. So the next quiz is on Unit 3. Actually, let me go and look all of this information up really quickly so I can give it to you correctly. All right, so I know the next quiz is on Unit 3, so that's going to be assigned tonight. And then the third quiz... Oh, I've already assigned the quiz for Unit 3. Okay. So it's online. It is due on the 27th. So, or it's due 26th. It's closed on the 27th. So make sure you get quiz number 3 in by the deadline too. And then the third quiz is going to be Units 4, 5, and 6, because you notice there wasn't really much content in this chapter. Unit 6 is going to be matter. And then I had the syllabus open. Unit 5 is the last time we need a calculator until we get to Unit 12. So, Unit 6 through 11, you're going to put the calculator away, and it's just going to be conceptual content. So, starting on next week on Tuesday, we're going to talk about matter. We're going to actually finally talk about chemistry. No more of this random math bullshit that sounds like, what the hell is this? This is supposed to be a chemistry class. Where's the chemistry? It's coming, don't worry. So Tuesday we're going to talk about what matter is, how we can represent it, and then on Thursday we're going to talk about what atoms are, and finally bust out the periodic table a few days after that. Okay? Make sure that you are getting everything that you need to done by the deadlines that are being posted. So that lab and quiz are due tonight. They will close tomorrow night, so make sure you have everything in by Friday. I don't accept late work without the NQA coupon. Other than that, have a wonderful weekend. I will see you again next Tuesday for Unit 6, so look forward to that, I guess, and hit me up in the Discord or email if you have any questions. Take care, and I will see you then. Cheers.